Stratospheric aerosol injection (SAI), also known as stratospheric aerosol intervention, is a geoengineering or climate engineering approach that uses tiny reflective particles or aerosols to reflect sunlight into space in order to cool the planet and reverse or stop global warming. It aims to mimic the cooling effects of volcanic eruptions by injecting sulfur dioxide directly into the stratosphere, where it forms sunlight reflecting sulfate aerosols. A research project that has introduced this technology is ScopeX with the Stratospheric Controlled Perturbation Experiment. The experiment involves the usage of a high altitude balloon to lift an instrument package approximately 20 km into the atmosphere. Once it is in place, a very small amount of calcium carbonate will be released to create a perturbed air mass roughly 1 kilometer long and 100 meters in diameter. The same balloon will then be used to measure changes in the perturbed air mass, including changes in aerosol density, atmospheric chemistry, and light scattering. The scientific balloon is fitted with repurposed airboat propellers which serve as an experimental beaker where gases and particles can be added, and it helps reposition the gondola to different locations. The advantage of the propelled balloon is that it allows for accretion of a small controlled volume of stratospheric air and observes its evolution for over 24 hours. The most considered and heavily researched aerosol for SAI is sulfate, which has been extensively modeled using various climate scenarios and investigated using data from previous volcanic eruptions, which serves as an analog of the climate effects of SAI. Research has determined that SAI will not only decrease global temperatures, but likely have direct impacts on ecosystems and public health. SAI will impact global public health outcomes related to hydraulic cycling, atmospheric chemical cycling, frequency of natural disasters, food system disruptions, and ecological health through the pathways of water, air, soil, and biota. The photo I have chosen shows a select major impacts and pathways of importance of SAI compared to unmitigated climate change. Light blue boxes indicate a primary pathway of SAI impacts, green boxes indicate a primary impact of SAI, while dark blue boxes indicate a secondary impact. SAI is feasible with existing technologies which can be implemented in a very short period of time and at a relatively low cost. Since stratospheric aerosols naturally fall out of the atmosphere, the benefits effects of this approach are temporary, generally lasting between 1 and 2 years. SAI is relatively inexpensive, costing only about $18 billion per year for each degree we want to avoid. Putting this into perspective, we can potentially avoid 1.5 degrees Celsius of warming by spending about $27 billion per year. This funding comes from the US government and has been the most important public funding source for financing research and modeling of SAI on a global and regional scale since 2008. In 2019, the US government allocated $4 million to the National Oceanic and Atmospheric Association, NOAA, to conduct research on solar engineering, that being SAI as one of the approaches. As SAI research continues to advance, both governments and organizations are increasingly recognizing the potential implications of this technology. This has led to policy discussions, and international collaborations to establish guidelines, regulations, and agreements for the responsible development and deployment of SAI, and a call for more research. Besides governments and organizations' approval, engaging people and raising awareness about SAI is needed. By educating people about the potential benefits and risks of aerosol injection, we can foster informed discussions, build public support, and ensure that any decisions made about SAI implementation are based on a solid understanding of the underlying science and its potential consequences. For example, the Make Senses team gave out balloons filled with chalk, dust, and helium in a park to educate people on SAI. The decision to use this technology would be a decision to intervene in the natural process of the planet and manipulate its climate, which raises the question of who should have this type of power. SAI, the idea of spraying sulfur dioxide into the upper atmosphere to cool the planet, is one of the most controversial topics in climate science, with scientists split in between. Supporters of SAI argue that it serves as a critical tool to save lives from some of the worst effects of climate change, while people against it argue that researching SAI risks legitimizing a solution with potentially catastrophic risks. A consequence of SAI would be a negative impact on the plants and crop yields. Since SAI decreases or scatters incoming solar radiation, many plants will receive less direct sunlight, which they use for photosynthesis. This could result in less food production globally, and with a growing global population, this may lead to future famines and resource conflicts. Additionally, fewer plants and biomass would reduce the planet's ability to absorb GHGs, which could further exacerbate the effects of climate change. Other potential unintended consequences of SCI include adverse health effects for humans and animals due to the irritant properties of sulfur dioxide and risks of increasing the acidity of rain, mist, and waterways. It's also unclear on how SAI would interact with other pollutants, buildings, and weather patterns on a larger scale. SAI offers a potentially powerful tool in the fight against climate change. However, its development raises complex challenges that must be carefully addressed. While SAI has the potential to reduce global temperatures and mitigate the effects of climate change, it also poses significant environmental risks and uncertainties. In conclusion, while SAI shows a promise as a climate change mitigation strategy, its deployment must be approached with caution. Effective risk management strategies, along with international cooperation and public engagement, will be essential for the responsible implementation of SAI as a climate intervention tool. Continuous monitoring and adaptability are crucial to ensure that the benefits of SAI outweigh its potential risks.